Good morning, everyone. It's Sunday morning, and I've already gone through and looked at everyone's test, everyone's exam two, and I know once again, you all didn't do as well as you hoped you did, but I've decided that I'm going to give everybody a 12-point curve on this particular exam. So, if you got an 88 on your exam, that means you'll get 100 on the exam. So, with that being said, this will be the solutions, uh, the exam two solutions video. Sorry, Sunday morning. You're just tired. Stayed up late, Saturday night kind of thing. Yeah. Anyway, so let's get on with this here. Okay. Let me make sure I'm in drawing mode. There we go. I need to pick the pen. Oops, unpicked it. Pick the pen. There we go. So yes, this is exam two. Okay. First question is a Bronsted-Lowry acid base. Oh, in a Bronsted-Lowry acid-base reaction, the conjugate base is defined as what? Well, this is one of those vocabulary questions again, right? And the answer here would be D. A product resulting from the loss of a proton, right? Because if you remember, you have an acid, which is HA, right? And then you have a plus a base, right? And this base has a lone pair on it, okay? And then it can turn into HB, right? And then plus A minus. And so what happened there is that the lone pair of electrons from the base pulled off that proton, resulting in an A minus because it lost the proton, leaving those electrons in that single bond between the proton and the acid to go to the acid, right? And that's why we get an A minus over here. And so your conjugate base then is this, the product that results from the loss of a proton. Next question. For the following reaction, identify the Lewis acid and the Lewis base. So if you look over here, you see that you have a chlorine right there, and you know that chlorine has a bunch of lone pairs. So it's got some lone pairs to give, right? But then you see aluminum trichloride, and there are 3 chlorines on that. So that's some, a lot of lone pairs are there too, right? But aluminum is a metal, and metals like electrons, number 1. And then number 2, if you look over here, the product is a partially positive chlorine, which means it lost an electron through sharing. And then the product has a partially negative aluminum, which means it gained an electron through sharing. Okay. What that means then is that the electron pair donor, EPD, is the chlorine, and the electron pair acceptor, EPA, is the aluminum. Okay, so that means then that the definition of Lewis acid is Lewis base is what? The definition of Lewis base is an electron pair donor. So chlorine is the Lewis base, and then the Lewis acid is an electron pair acceptor, right? And so that's the Lewis acid. The only one that matches these two things is number 1, or number A, letter A, and so that would be the answer. Which of the following best describes the Levy effect, right? So this focuses on that one slide I had when I was talking about how water can't be used as a solvent when it either has when the base in the reaction is stronger than hydroxide, right? Or when the acid in the reaction is stronger than H3O plus. Okay, and the reason why is because you don't want the water reacting with the reactant before, as a solvent, reacting with the reactant before the reactant reacts with the other reactant, right? So then the strength of the reactant, in this case an acid or a base, is diminished because it's already reacted with the water solvent instead of the intended reactant. The only answer there that best fits that is E. The limiting of a compound's acidity or basicity by respective deprotonation or protonation by the solvent. Right? And in my example, I used water in the slides. Next, number 4, which of the following best describes if sodium amide is suitable for reagent as a reagent for deprotonating this compound, right? Well, the first thing to notice is that sodium amide, right, on the chart, the acid-base chart, right? I can't remember what its exact pKa is, right? Because I don't expect you to even remember what the exact pKa is. But it's like around -7 to -9 or something like that, right? So, and the reason why it is like that is because when it breaks apart to sodium plus and the negatively charged amine, or also known as the amide ion, not to be confused with the amide functional group, it's got 2 lone pairs on it and a negative charge, making it super basic. And then this guy here has 2 protons here. You might be wondering, why is it not that proton or that proton? Well, that's there. Well, the one that's between the resonating oxygens are going to be the most acidic, right? Because remember, in ARIO, resonance stabilizes a carb anion, right, or a lone pair. And then so we have here the proton being taken off by that lone pair, and then this can come up here, or it can come over here, right, and make these go up like this, delocalizing them, right? So the best answer here will be yes, the resulting conjugate base would have delocalization of charge over 2 oxygens, like I just showed you there, whereas the sodium amide has a localized negative charge, which is which is what you see right there. All right.
Siri here. Let me know if I can help.
Thank you, Siri. I really didn't need you right there, but all right. Okay, Siri, you need to let go. There we go. That was weird. Siri's taking over the world. Alright, rank the indicated protons in decreasing order of acidity. So you can do 2 things here to figure out what this is, right? What the answer to this is. Either have memorized the approximate ranges of the pKa's on that chart, or just use ARIO. Okay? The one here that has the most resonance destabilization for a lone pair, right, is going to be the proton that's denoted by arrow I, or arrow 1, right? And the reason why is because you have a base come over and you take off that proton, that bond goes there, that goes up there, right? And then you end up with an alkoxide? No. What did I call? Oxyanion, right? Right? So that's some really good resonance there, especially since you have the oxygen, right? Because it's electronegative. And since it's also electronegative, it also fulfills the I part, induction, too. Okay? Whereas over here, you have an alkane proton, right, with no resonance, right, and no induction, no nothing right here. It's just an alkane proton. And then the pKa of this alkane proton is like, geez, like 50 or something, 40 or 50, right? So you already know that this will be the least acidic right here, right? So that 3 will be last, 1 will be first, right? This, when you pull off this proton with a base, it does do resonance. This negative charge here will go down here, and that will go there, and it will go there too. But the reason why it's in the middle and not the first one is because you have an oxygen over here, okay, facilitating that resonance. So the answer with this one will be A. 1, 2, and 3. Well, for the first time, it's actually in the order that it's supposed to be in, numerically. Okay, next. Number 6. Identify the reaction, identify the acid base and the acid and base, and provide curve arrows for the mechanism, right? The correct curve arrows. So here you quite simply just see what arrows are going in the right direction, right? And which one is the acid and the base based on, you know, who's losing the electrons and who's gaining the electrons, and you got the answer, okay? So you already know it can't be number 1, structure 1 right here, okay? Because you can't move a proton. You can only, and this arrow here makes it look like a proton is going towards those electrons. 2 protons don't move. Electron pairs move. So in fact, right, that's wrong. This second one is the same thing as the first one, right? So it's wrong. And it also has an electron pair coming over. I don't even know what the heck is going on there. That doesn't make any sense. So that's definitely wrong. Oops. Oh, I just maximized it. You probably needed that before. My bad. Then the next one here does have the base, right? The Lewis base here, donating some electrons over to the water acid to pull off that proton. But the problem is that you have two arrows pointed at each other, and that's a bad no-no, right? Because that arrow should actually be pointing towards the oxygen, making the hydroxide ion. So that's definitely wrong. That's a no-no. Then you have this problem here where that's making the proton move again, not the electrons. But then also you have two arrows going two opposite directions, and that's incorrect as well. So the only one left is this one, structure structure 5. The base here, the lone pair on the alkyne right here, is coming over to pull off that proton, and the bond between the proton and the water goes to the oxygen, making the hydroxide. So that's answer V, or I, or answer 5, structure 5. Okay, what is the IUPAC name for the following compound? So you have a cyclopentane here, right, because it's a pentagon, but then the tricky part is naming where the substituents go. It's not that tricky though, because you want to do it so that the highest alphabetical letter, right, is first, and so that's ethyl, methyl, and methyl, right? So obviously the ethyl comes first because its E becomes for M, right? So you'd number there 1, 2, and 3, 4, and 5, right? So it would be 1 ethyl because there's only one ethyl, right? 2, 3 dimethyl because there's 2 methyls, and then cyclopentane. So 1 ethyl, 2, 3 dimethyl, cyclopentane. The answer there would be C. Next, identify the size of a hydrocarbon that is used in gasoline. This is just something I just kept on telling you over and over and over again in lecture, which is gasoline is isooctane, right? Octane is how many carbons? It's 8. So that's B, 5 to 12. Next, which of the following is the correct Newman projection for the following compound as viewed down the indicated bond, right? So this is one of those things where you've got to think about this three-dimensionally, especially since you probably don't have a Milker model kit at home that you're looking at, and plus you can't use one on the test, right? You're looking down this bond, right? Right here, which means that bond, that flat bond, is where the flat sheet of paper is, okay? So pick up that bond, look at it, right, with the piece of paper going up and down like this, right? And then you'll notice that whenever you have a wedge bond coming out, right, a solid wedge bond, it's coming out of the paper on this side, right? Well, for me, it's coming out on this side, the left side. But you see a mirror image of me, so it will be coming out on this side. But the point is, when you pick up the piece of paper and you see a solid wedge bond that's coming out of the piece of paper, in fact, when you're looking down the bond, it's going to the left side, okay? And then you have a dashed wedge bond, right? It's actually coming out on the right side, okay? So this guy here should be where? The solid wedge bond. It should be on the left side. And this guy here should be on the right side, okay, of the Newman projection. And then the other thing to note here is that you have two ethyl groups that are also in the plane of the paper, which means they're going to be opposite each other, right? Completely opposite of each other, right? So you can already eliminate a whole bunch of things just from the fact that you have those two things knowing one's on the left, one's on the right, and then the opposite ethyl groups, okay? Opposite ethyl groups. So it can't be this one because that's ethyl opposite. That's ethyl opposite methyl. Can't be this one. That's ethyl opposite hydrogen. Can't be this one. That's methyl opposite opposite. Methyl opposite methyl. And it can't be this one because that's methyl opposite hydrogen, right? So the only one that it could be is structure 3. So let's just check though. Is the methyl group over here pointed downwards, coming out on the left side? Yes, right there. Is the methyl group up here pointed upwards? Coming out on the right side? Yes, right there. So the answer is C, right? The answer is C. So that's a really easy way to figure this out, okay? Since that one was so easy, I did give you a slightly trickier one here, okay? Oh, hold on. Where'd it go? I did give you a slightly trickier one here. What is the what is the correct structure, right? Wedge dash structure for this guy? And the reason why it's a little tricky, right? And your biggest clue here that as is, none of those answers work, right? Is because over here you have two bromines on the same side, okay? And they're on the right side, so they should be going towards the back of the paper. You have two hydrogens on the left side, right? And they should be wedges going towards you, okay? Because on the left side, right? And as you can see, none of these have bromines on the same side. None of them do, okay? None of them do. So at this point, you're thinking to yourself, oh, I remember what Dr. No said. He said that you can have rotation, right? That's what a Newton projection is. Remember? When you rotate around that single bond and you get like the eclipse and the staggered and the anti and the gauche and all that, right? So these must have been rotated, right? So you can spend a few minutes and go through and rotate each one like one way and see if it matches, right? When I took the test, right, I always, I'm one of those that always thinks C is the right answer. So I started with C. I will, fully admit that this will take a few minutes to do, but the other ones are so fast that you should have made up time to do this one. And if you take C and you rotate it rotate it about that bond, right? And you're looking down this bond right here, as always. Okay, you're looking down that bond right there, as always, right? Then you'll see what I'm talking about. So I'm going to remove the eyeball, but just remember that this is the direction you're looking, because I need a draw there. It's taking a minute to erase this eyeball. There we go. Okay. So think about it. I have a proton here that's wedged out right now. Okay. Okay, I have a proton that's wedged out. Oh, not a proton, sorry, a methyl group. I have a methyl group that's wedged out. And if I rotate the bond just one substituent over, what happens to this methyl group? It moves it up here, right? It moves it to where the bromine is. Okay? Then, if I rotate the bromine, so if that methyl group moved up and then took the place of the bromine, where did the bromine go? Well, it comes down to the back of the page, right? It comes down to the back, like that. And then what used to be there where the bromine is now? What used to be there where the bromine is now is just the proton that was there before. Okay? And then you can go ahead and draw the solid wedge proton that was over here. And notice what happened, right? Now you have both H's on the same side. Right? Now you have both bromines on the same side. And then you have methyl groups both flat in the plane of the paper opposite each other. So the answer is C. And again, it's going to take you a few minutes to rotate through, but honestly, you could have just rotated through the first three and got there, right? Rotate it once to figure what it is out. Next, consider the graph of the conformational analysis of propane. That's important to know. The structure here is propane, okay? And what does the arrow indicate? Right. Well, the first thing to notice is that it can't be A, because A has one carbon in the front there. It's a Newman projection, so it has also another carbon back there behind it, because you're looking down that bond, and it has two carbons on the side. That makes that a butane. right? Not specifically butane, right? But it's got 4 carbons, so that's a type of butane, okay? So it can't be that one. Then look at this guy here. This guy only has 2 carbons. One here in the front and the one that's back there behind it, right? So it can't be that one because that's an ethane. Okay. Oh, good. We finally have over here a propane. We have another propane, right? 1 carbon there, on the substituent, and then 2 in the axis of the bond on both of those on 3 and 4, or III and IV. But then over here, that can't be it either because you still, again, you have 1, 2, 3, and the one behind it. So that's 4. That's another butane. Type of butane. That actually is a butane. Whereas this is like an iso, not an iso, it's like a butane, but it's like a tert-butyl, right? So none of those. So you're only left with these 2 right here. These are your 2 only options here. They're actually propanes, okay? Got to read the question and remember, it's asking for a propane. Okay? And then the next thing is, remember when I was talking about having an eclipsing anything, right? Or not eclipsing, but like a conformational analysis where you're spinning around the bond, right? The highest energy is always when the substituents are about to pass each other and they're eclipsing each other. So this structure here is indicative of the highest energy up here, right? Because energy is on the y-axis, the lowest energy is down here, highest energy is up here. So this guy here, in the eclipsed, is the peak. Because when you eclipse each other, there's steric hindrance, and so there's more energy. So that means then the only other answer is this, because right now they're staggered, and staggered is the lowest energy when it comes to the rotation of the sigma bond between a propane. Right? So the answer here is C, or structure III, or 3. Okay, next one. Which of the following has an axial OH? Well, we only talk about axial OHs when we have boat or chair conformations. And the ones here, 3 and 4, are not in chair or boat conformation. Okay. And then axial we know means up and down. So that right there is equatorial, that right there is equatorial. The only one you have left is this one. So it's answer I, or A. Next. Which of the following is the highest energy chair conformation for the following cyclohexane? Remember what I said about this. The lowest energy is the one where the most are in equatorial. So, the opposite would be true then of axial. The highest energy would be the one with the most in the axial position. The only one that has all 3 in the axial position, structure 3, which is C. Okay. What is the relationship between these 2 compounds? These 2 compounds are clearly constitutional isomers. A. Why? Because they have the same formula, but they are different constitutionally, or they're different in the way they're connected. The atoms are connected. Okay, next. Singular. I actually take singular, so this is particularly close to my heart. Okay. It's asking, what is this? Cis, trans, or neither? For this bond right here, it's the only one that has that possibility, that double bond right there. They're opposite each other, so clearly that is trans only. Okay. Indicate which has the chiral center, right? And nicotine here. I don't smoke, so this one doesn't touch my heart, right? Not like singular does. That's because I don't smoke. But, right, the only one here that has all different substituents, right, is B. Because it has a nitrogen, it has CH2, it has a CH2, it has another CH2 but an aromatic or a double bonded CH2, right? You'll learn about aromaticity in organic 2, possibly for me since I'm teaching that in the fall. And then remember that we also have a proton right there too. So 4 different substituents means that B is the only one that is chiral. Okay. Next thing to do is assign whether or not this is R and S, right? The configuration is the chiral center is R and S, so we're talking about the one that's connected to the oxygen right there. Okay, so the first thing to do is do your numbering. We have 1 right there. because O is bigger than both oxygen. Sorry, oxygen is bigger than both, not bigger, but like, oh, higher atomic number than both carbon and the proton that's back here. Which is actually really lucky for us because the proton is already, or the hydrogen is already pointed backwards, so we don't even have to rotate it. Okay. And so the next thing to do is, since we have both carbons here, right, we'll go to the next layer, right? We'll go to the next layer. This carbon here is connected to another carbon, and a hydrogen, right? And another hydrogen. Whereas this carbon here is just connected to... Oh, I wrote that backwards. I apologize. This one is the one that's connected to... This carbon here is connected to 3 hydrogens. Right? It's connected to 3 hydrogens. And then this one here is connected to a carbon, right? And 2 hydrogens. Right? So carbon here beats this hydrogen over here. So this is number 2. Okay? And this is number 3. Okay? And again, don't forget what I always say, because I promise you RNS will come up more. Configurations will come up more, right? It doesn't matter where the H is, because it's always in the back, and it will always be last, right? So just count the 1, 2, and 3. 1, 2, 3, right? And the 4 is in the back. We're going clockwise, and so that means... Oh, that's the name of excuse me. That's the name of the channel with Vampire Diaries and the originals and all that, right? It's the only shows I watch on that. I revealed something about myself that I didn't want to reveal just now, but maybe I've already revealed it before, so maybe it's okay. But I did watch Vampire Diaries and the originals. Anyway, sorry. Has anybody watched the new one yet? Like the newer one, Legacy? Is that good? I have no idea. I haven't watched it yet. Although it's supposed to have Alaric in it. I really like Alaric, so he's a cool guy. I cried when he died in Vampire Diaries. Anyway, so this is clockwise, so it's R. I mean, it's R, but the answer is actually A, because R is not a choice. The answer is A. Next, same thing again for Cymbalta, medication used to manage depression. Okay, but this time we're not so lucky, where the hydrogen is like, it's actually coming out at us this time. Right? So we're going to have to rotate it after we get done numbering things. Okay? So let's number things. Of the first level of atoms connected to the constituents connected to that carbon right there, the chiral carbon, of course, oxygen again gets 1, and hydrogen gets 4. So now it's between this carbon and this carbon. Okay? Excuse me. So we know then that sulfur, this carbon here is connected to a sulfur and a carbon, right? And then this one over here is connected to 2 hydrogens. And a carbon, right? So sulfur beats carbon, making sulfur the more higher priority. So it's 2, right? And then 3 for that carbon right there. Now we've got to flip it around, which I wouldn't recommend flipping the whole thing around. I would just draw the part that matters, which is everything from here to here, right? And then here, okay? No, I'm sorry. I meant to do it from... Oh, I can just do undo because that was the last thing I did. There we go. There, right? And then there. Okay? And in fact, you've already got the damn, the priority, so you don't even have to draw the extra stuff. So I would just draw it like that. Right? So now oxygen's on this side, because you flipped it around. Okay? The proton is going backwards now into the paper. This carbon up here is coming upwards now. Right? And that was a carbon. Okay. And that was carbon 3, remember that. That was already labeled 3. That was 1. And then on this side we had the carbon that was connected to the sulfur. right? The sulfur. Well, I guess just to make sure it's consistent, right? We had this here. Oh, erase, undo, 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 undo. There we go. Undo, 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 undo. There we go. It's actually supposed to be like this. There we go. That's the one that's 3. This carbon right here. Right? Just so you don't get confused. That's 3. And then the sulfur down here. And it had stuff it was connected to too, but we don't care about that stuff. Okay? And then it, like that. Okay? So now it's flipped around. Yes, this is a CH3 right here. Okay? So it was 1, 2, 3. Now we're going this direction. Right? And correct me if I'm wrong. That is counterclockwise. Right? Because up there we were going towards the left at the bottom. Now we're going towards the right at the bottom. Alright? So, since it's going CCW, the answer is S or B. Good stuff. 19. Which of the following is the correct structure for S3-methylheptane? This one's, it's a little bit more, it's a little difficult, but notice that you have a heptane there. Both of these are hexanes, so those are wrong. So it's between this one, between these two right here. Okay. So what I would do now is I would just go through the first one and see if that one's either R or S. And if it's R, then number 2 is the right answer because that's the S one. But if it's S, then number 1 is the right answer. Okay. So let's go through and do this bad boy. Name its properties again. So the only one that we really know right now, without going to the next layer, right, is that you have, luckily for us again, the hydrogens in the back already. That's another reason why I picked the first one to do, because you don't have to flip it around, right? But we know that that's 4 already. Okay. So up here we have a methyl group, which we have a carbon and a carbon and a carbon. Right, now we've got to go to the second layer because they're all 3 carbons. Okay. This carbon is connected to 3 hydrogens. Okay. This carbon right here is connected to another carbon, a hydrogen, and a hydrogen. And another carbon, and a hydrogen, and a hydrogen. Okay. Got it? Was that right? 1 carbon and 2 hydrogens, right? 1 carbon, 2 hydrogens, right? So the only thing you know now is what 3 is, because 3 is this one. This hydrogen up here actually loses to both of those carbons. Okay. Next thing is that since we have a tie here and here, we have to do another tiebreaker. So now this carbon right here is connected to what? It's connected to 3 hydrogens. And then this carbon right here is connected to what? A carbon, a hydrogen, and another hydrogen, right? So now the priority goes to here. We know now since there's only 4, we need number 2, right? Number 2 is going to be over here. That's the next one. We're going backwards, basically. And then the highest priority would be number 3 over here. Or, sorry, number 3, but this one on this side. Because the hydrogen over here loses out to the carbon over here, right? So again, hydrogen's in the back. We don't really care about it. Just count the 1, 2, and 3. 1, 2, 3. Right? We're going clockwise there, right? So this is an R, which means it can't be this answer here. That makes this the S. Okay? And you can check that if you want to, but remember what I said before. If you want to just change from R to S, you just make the constituent that is pointed outwards, pointed backwards, right? And that's how you make the switch between the R and the S configurations. Excuse me. Next. Which represents this guy right here. Okay. Which represents this guy right here. Let me just make it so you can see the whole thing. Okay. So the first thing to notice here is where everything is. Okay. Where everything is. And the way we're looking at this particular thing is we're looking down the bond that has the chlorine and the bromine. Okay. So we're looking this direction here. Okay. Excuse me. And then the next thing to notice too is that the bromine, right, is actually in the plane of the paper. It's not going out of the paper or into the paper. So you can already rule out this guy here because it has the bromine going into the paper, going backwards into the paper. Okay. Next thing to notice then is that the chlorine, right here, is opposite the hydroxide or hydroxyl or the alcohol. Okay. So we need one that looks like where the chlorine is. So if you're looking at like this, right? You picked it up and you looked it up like this, right? The chlorine, when it's coming out at you, right, needs to be opposite the the hydroxide. It cannot be this one because that has the chlorine and the hydroxide on the same side. And it cannot be this one already because that has chlorine and oxygen on the same side. And it can't be this one here either because that has the chlorine and the hydroxide on the same side. Okay? So it's between these two. So all you have to do now is figure out which one has the right configuration. Is that the S on the left or is that the S on the right? Right? Because both these are the same thing. It just has the R and S labeled on different sides. So again, just pick one first and just do it and see if it's right. And if that one's not right, then it's the other one that's right. Okay? So this is claiming that this is S. So let's go ahead and just label these and do our thing here. And luckily for us, we already have the hydrogen. The other reason why I picked this one too is because the hydrogen, well, both of them have the hydrogens going backwards, but whatever. So here's the hydrogen going backwards. Okay. And let's go ahead and label our priorities. Okay, let's go ahead and label our priorities. Bromine has the highest priority. It's the highest molecular weight, highest atomic number. There it goes. Chlorine comes after that, and then carbon right here comes after that, right? And then hydrogen hits 4. Okay. So 1, 2, 3, 4. We're going counterclockwise, which means this is an S on this side, right? And this is correctly labeled then as an S, which means the other one must be R, which means this one is incorrect because it's saying that this is an R on that side and it's not. So the answer here is structure I, or 1. Oops. Okay. Next one, number 20. If a sample of carbone, which I still don't know what carbone is, and nobody answered me in the video about what carbone is, but I don't blame you because you had an exam and yeah. But if a sample of carbone gives a specific rotation of 0 degrees, and the specific rotation of pure R carbone is negative 61, then what is this? What is the configuration of the unknown sample, right? Well, remember that in an optically active compound, right, the R version will make it go some number of degrees one way, either positive or negative, and then the S version will make it go some number of degrees the other direction, the opposite direction, but it will always be the same number of degrees. Okay? So in the case of carbone, the R goes negative 61 degrees. The S version goes how many degrees? 61 degrees from 0, right? So if the specific rotation of the compound is 0 degrees, right? That means that you don't have any extra R or S, right, to push it from 0 to 1, 0 to the next, or the other way direction, right? Because the negative 61 and the 61 cancel each other out. And that's why the specific rotation is 0, right? And what that means then is that we have a racemic mixture. Because a racemic mixture is a 50-50, 50-55? No way. A 50-50 mixture, right, of R and S. So the answer here is C. Next, what is the relationship between the two following structures? These are definitely diastereomers, right? They're not constitutional isomers. Oh, I'm sorry. I think I did that wrong there. They're not diastereomers. They're actually enantiomers, right? Because they're not diastereomers because they are non-superimposable mirror images. These are mirror images of each other, right? If you were to put them face to face with the OH on both sides at the same side, right, and they are mirror images, but they are non-superimposable mirror images, right? So because of the chiral center right there, so it's definitely enantiomers. Can't be constitutional isomers because constitutional isomers just have the same formula, not the same structure. But then the question then is it a diastereomer, right? Well, diastereomers are non-superimposable, yes, but they're also not mirror images either, and they're definitely not identical. So see, that's what happens when you read these things too fast, right? The answer here is A. Next, which of the following choices represents the Fisher projection of the following compound, right? Well, this is again one of those things where, like, none of these actually fit the structure drawn, okay? Because if you were the one that you may think fits it is this one. Well, it definitely isn't this one here, right? Because it has an odd number, right? Can't be that one. And it can't be this one because this one has two hydrogens right here, right? When all four carbons have hydroxyls on it, right? Can't be this one too because it's like an even number on the right side and the left side over here. So it can't be 1, 3, and 1. That can't be right either. So it's really between this one and this one, okay? But if you notice though, right, the OHs on the left and on the right are not pointed in the right direction for it to resemble it going up out of the paper and then into the back of the paper, right? So this is another one of those things again where you have to rotate it about this single bond. And when you rotate it, all these OHs become on the same side because they become wedges, right? And so the correct answer is this one. Don't forget that you can rotate around a single bond. Okay. Next, we have allene, right? Allene. So remember, whenever there was only one slide about allene in the lectures, and in this slide, I said that if the two constituents, right, are different on the end of an allene, right, then those are definitely chiral centers, even though there's only 3 bonds there, or three constituents there. They're definitely chiral. That's the first thing to say. And the second thing is that they have dash wedge bonds that are opposite each other, right, of the constituents, and so that makes them mirror images, and then they're enantiomers, right? That makes them non-superimposable mirror images, and they're enantiomers. And then we're to the last question here. Is this an E or a Z, right? Is it a Zuznamen or an Intigen, right? Quite simply, we just need to figure out which ones are the highest priority, and then if they're on the same side, right, they are Zuznamen, which means together. But if they're on opposite sides, they're Intigen, which means opposite, I think. Okay, so this is really easy because these are both H's, right? And so they're competing, those H's are competing with a carbon right there. Carbon always gets the priority, so 1, 1 of this group and of this group. The ones are opposite each other. And your instinct here is to go with Z because Z looks like it, right? It looks like a Z, sort of. But no! Right? In German, though, right? Intigen means opposite, E. Okay? And Zuznamen means together, Z. So the answer here is E. Yeah. I used to have an organic professor, Dr. White. He was German, and he was actually in charge of this class, where we spent the whole summer in Germany, learning about chemistry. It was in the summer. It was great, and he was very adamant about this. He was very emphatic about E and Z because he was German, right? That crazy guy, crazy Dr. White. We used to have this thing called the White method in lab. And it's not anything like extraordinary or mind-boggling or anything like that. But I'll tell you about the White method later on in the semester. You put a pin in that. To be continued. All right. Well, that's the exam. and I'll go through and add 12 points to everybody's exam, and then I guess I'll see you tomorrow on Monday for the next lecture. Good luck, and have a good rest of the weekend, right? Because we still have the whole day of Sunday, and it's actually sunny. I spent some time outside yesterday in the pool, and now I'm a little darker. Yeah. So, but I had this little farmer's tan going too because I was always wearing my shirt and outside and it was really sunny and stuff like that. So, it's good that I got in the pool because now the farmer's tan is gone, right? Anyway, see you tomorrow for lecture.